Thank you. Yeah, so this is a brief outline about the topics which I'm going to cover. Initially, I'll give you some introduction about your learning and some basic idea about what basically machine learning is, some related terms, and a brief history about this machine learning, because it used to be there among us, but we were not aware about it because we thought that, okay, this is something which is a normal practice. But I'll show you some of the examples that would make you feel that, okay, this is something which was there with us. And then we'll talk about supervised learning, where we'll see classification and regression problems. And I'll also throw some light on your semi-supervised learning. Then we are going to talk about these many topics. So I'll quickly jump to this. So what I have done is I've created this word cloud that contains all possible, to the extent, in fact, all possible keywords which will be used in machine learning and deep learning area, where you will be dealing with your networks, you'll be dealing with your decisions, programming, functions, and then we have vectors, we have support vectors, and obviously we are dealing with machine learning problems. So I do have to talk about probabilistic theory as well. Then we have several models and so on and so forth, right? So this entire thing is in fact, I would say a subset, because each day or every month or every week we get a new model, right, available to us. We started with some basic statistical processes, right? And if you talk about today, we move to machine learning, and we then move to deep learning. And there also we have moved to the stage where we are dealing with GAN, we are dealing with BERT, and so on and so forth. In fact, some of the things we will be covering in this refresher course as well. Now, so to start with, what basically the learning is, formally speaking, learning is any process by which your system will improve the performance. And this improvement will be just because of the prior experience, right? So this definition is not by me, it's by Herbert Simon. And when we say learning, right, it can be it can be a heuristic approach as well, which tends to great learning, right? So this becomes a process of acquiring new understanding, right? And along with it, I can acquire some knowledge as well. And if I'm talking about knowledge, so definitely I'm dealing with some new skills as well. I'm adding some values, I'm adding some behaviors, right? And that's what has given a rise towards machine learning, because we thought that let machine also gain all these new understanding, this knowledge, this skill, right? So now the point is that how old this learning is, right? In fact, how old this machine learning is. This is something which is a familiar object, where you have your OCRs, right? OCRs exists. OCRs are with us since ages, right? So basically your machine learning is not just a futuristic fantasy, right? It's already here. And in fact, I would say that it has been around for decades for some of these specialized applications like optical character recognition. Here also, it is, in some sense, we are talking about your machine learning only. And not only this, I have another example with me where I can say that machine learning was playing some roles behind the curtains, right? So this is your spam mails, right? So in this, what we have is that this is, I think, probably one of the first official formal ML application that really became a mainstream, because This has obviously improved the lives of hundreds of millions of people, and this was available from early 90s, right? So this spam filter is basically approaching a category of problems which is your classification, right? And that we'll talk about the classifications in next few slides. That means we are directly dealing with your supervised learning. Don't worry about what basically the supervised learning is. That would be clear in next few minutes, right? So your spam filter, it used to exist, and over a period of time these spam filters have become smarter and smarter, right? It has improved a lot. And these days, not only simple flagging works, but apart from that, not many backend processes takes place, right? I'll explain some of the things in the coming slides with the help of some of the examples. Sorry. Just a second, some technical glitch. Yeah, sorry for this interruption, right? All of a sudden this malfunctioned. Now let's take some definitions on machine learning. So this is a very popular definition by Arthur Samuel. It was given in the year 1959. So this says your machine learning algorithms enable the computers to learn from the data, right? Because computer needs to have some base, right? And that base will be this data, and further improve themselves without being explicitly programmed, right? So this term, right, or this explicitly programmed, I have used multiple times because it is not always that I have to write all those rules which used to be there in 80s and 90s, based on which my entire system is going to work. But this time I have some more expectations from my computer system or from the machine, right? And when you listen to this term machine learning, a picture comes to your mind which will be of, let's say, a robot, or it will be from, let's say, a Matrix movie, right? Or it will be from your Terminator, and so on and so forth, right? But whatever has been shown in these movies, it's in some sense dealing with your ML and DL applications. But what is happening at the back end, we need to analyze that part, right? This was a basic definition and a very popular one. Let's take a step ahead and see another formal definition given by Tom Michel in the year 1998. So it's 1998, right? So it's like we are very close to these dates, right? So basically, your machine learning is the study of algorithms that would improve the performance P at some task T and with an experience E. So it becomes a well-defined tuple with P, T, and E, right? So it says that a computer program is set to learn from the experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. Probably I might have confused you instead of convincing you with this definition, right? Dealing with these E's, T's, and P's. But still, let's take another definition, a very simple one, right? So that would be in a very simple machine learning definition in layman's language. What we have is we feed the data to the computer, let it learn something on its own, once again without being explicitly programmed. As I said, I have used this terminology several times. So one of the example can be a small child, right? This small child has no clue about this outside world, but slowly and steadily, this kid looks at, let's say, banana, looks at apple, and over a period of time gets to know that, okay, this fruit which is kept on the table is either apple or banana or orange or something else. Right. So what kind of data we are feeding? It's the image which this kid is taking, image of these bananas, or or the actual banana you can say, or actual fruit you can say. And at the end, without being explicitly programmed or trained, I would say, this kid is able to identify and differentiate between what is a banana and what is apple or orange or something else. Right. So this is possibly one of the simplest way to explain what basically machine learning is. See, in some sense, I am trying to make my machine smart. Right. Machine here means my computer, right? Or it can be, smart devices. These days we talk about lot many smart devices, your handheld devices, which are your tablets, cell phones, your IoT devices, your healthcare devices, your wristwatches, smart watches, and these days you have smart chips as well, right? So we have reached to a different level totally. Now the question is like, when to use this machine learning, right? We got to know what basically the machine learning is. We got some basic definitions. Now the point is that when to use this machine learning technique, right? So let's say I have to navigate on Mars, right? And this is to be done by a robot. Here your human expertise does not exist. In that case, I would prefer to my system to take a call, right? That means my machine will take a call on navigating on Mars, right? Mars rover will be, hovering around the surface and will be taking some pictures, will be observing something. So it's all because that it's not like we are giving some continuous instruction that move 10 steps ahead and then capture something. It's all because this robot or the rover identified that there is something which is to be clicked or which is to be captured. Let's take an image or let's record a video and send back to the earth. Then we have like speech recognition, right? Where humans can't explain their expertise. Now, many times, let's say I don't know Chinese, right? But these days, let's say I know that there is an API and which I can program, and there is already app which can convert one language to other. Right? Your simple smartphones have the capability where you go for voice to text conversion. And you might observe even your keyboard, right, or keypad available with your cell phones are smarter enough. Slowly and steadily they get to know your way of typing or your way of giving some inputs. Then next time, if suppose I am typing, let's say JA, now immediately my keyboard will suggest that this can be one of the possibilities which you are planning to type, right? Just because my system knows that the current location is Jaipur and I'm continuously, even to share my address, I am typing this thing. So whenever next time I'm giving input as J and giving input as A, I immediately get this kind of output, right? And I select this and I save my time. So what I've done is I have made my system smart, right? Over a period of time, my handheld device has also learned how to react in a particular situation. Then in case of personalized medicines, of course, right, your model must be customized, right? In healthcare, your machine and deep learning applications, right? Lot amount of search is going on in this healthcare field as well. In fact, you might have heard that these days some of the basic operations are done by robots, right? Of course, under the guidance of experienced doctors, but at the initial level, these things are pretty successful. And not only that, some of the devices which are used in healthcare are also on a base of machine learning or deep learning. Then we have like genomics, where we are dealing with huge amount of data. And then we have like weather forecasting, where we are dealing with huge amount of data. So these are the models which are based on huge amount of data. That means, let's say I have to predict the weather for a particular place, and let's say their IPL matches are going to be organized, right? In that case, I need to rely on the forecast, and these forecasts are based on, previously these forecasts were based on statistical models plus the prior experience. These days you will find
Hello.
Sir, you are not audible.
Hello, Vikas.
yeah,
Vikas, can you? Yeah.
yeah. So that means for the entire duration I was not audible.
Yeah, sir. So since last 2 or 3 minutes, you are not audible.
Okay, since last 2 or 3 minutes. Okay, fine, 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 fine. I thought, I don't know why this happened. Uh, okay, fine.
I think we are not able to hear you again.
See, I think someone is, bringing me back to the mute situation. Am I audible?
Yeah, you are audible now. But when you start presenting, so then in that case, you are not audible.
Okay, just a second. Just a second. Am I audible?
Yeah, you are audible now.
Okay, fine. So initially I was talking about, the basic possible definition, where I said that feed the data to the computer, let it learn something on its own, once again, without being explicitly programmed. So ultimate aim is I'm trying to make my machine smart. Right. I gave you an example of a child where, this child is not aware about, if suppose I'm keeping, let's say, bananas and let's say oranges in front of this child, then this child is initially not aware about what kind of fruit it is or whether it is a fruit or not. After a period of time, maybe because of, we can say, some heuristic approaches or something else, this kid gets to know that, okay, this is something which is a fruit, and at a later stage gets to know that a particular thing is a banana and a particular thing is an orange. Right. So this child gets the understanding by looking at the fruits. Similarly, what I'm expecting is that my machine should be smart enough to deal with the problems. Now, the point is when to use machine learning, right? Let's say where human expertise does not exist, that means I have to, let's say, navigate on Mars. My Mars rover has to navigate.
Hello.
Sir, you aren't audible, sir.
Yeah, Vikas, sir, you are not audible again.
Yeah. So, Anand, whether everyone else has the right to, mute the presenter, because I feel that someone is, turning off this audio option.
Okay, so let me check. I think so that is not
No
possible.
sir, मीटिंग होस्ट मैं कर रहा था एंड मैं अभी ऑफ तो कुछ नहीं कर रहा हूँ अभी.
Since you are the host, then this should not be a problem. I don't know why it is happening continuously. Let me see with another device. I'll switch on the audio options of a different device.
Okay, sure.
Yeah. So I hope I am audible now.
Yes, you are audible now.
Yeah. So what I'm doing is that I'm presenting with the same device, and I'm using the audio and other facilities of a different device. Let's see how it works now. Yeah. So I was talking about when to use machine learning, right? Probably I'm explaining it for the third time, but anyways. So when, let's say, the human expertise does not exist, right? So I have a Mars rover, and it should not be a case that every time I have to feed it that, okay, move 10 steps forward, then click a picture of the surface, send it back to me, right? This rover should be smart enough to travel on the surface of Mars, and wherever it observed something interesting, should capture the image or take a video and send back to me, or send back to the Earth surface, right? That kind of expertise I am expecting. Yeah, that kind of expertise I am expecting from my machine. Your speech to recognition is one of the examples, right? These days, your smartphones are smart enough to convert your voice to text, right? And not only that, even your keypad application is smart enough to take care of your typing, right? Let's say if suppose I'm using my cell phone and I'm planning to type Jaipur, the moment I'll type JA, it will suggest me several options where Jaipur will be one of the options, just because my application knows several times I've used this term in order to send my address details to someone else. Plus, on top of it, my location is also Jaipur currently, right? So that kind of smart my keyboard or keypad applications are these days. Now, another thing is that if suppose I have to come up with a payroll management application, in that case, I don't need any machine learning application, right? I simply don't need any machine learning application because I know these are some simple steps. For that, my machine should not learn anything. It should only calculate based on 2, 3, 4 formulas. That's it. Right. So in some sense, learning isn't always useful. Right. Learning isn't always useful, but I'm not saying that it should be in every case, but yes, in some cases. Right. So now the question arises, why I should use machine learning, right? See, recall our previous days is where we used to write and used to depend on the rule-based programming. Now, for a simple chess game, or even if suppose I have to come up with a Ludo game, right? I have to plan it, I have to write several rules for it, and entire rule-based engine will be working behind this application, thousands lines of code with not the optimal solutions, right? So in that case, I would prefer to have a machine learning algorithm at the back end, which is not explicitly programmed. Once again, I am focusing on not explicitly programmed and yet taking some decisions. In fact, you can look at the spam, right? What it looks like. You might notice that some of the things continuously go to your spam. It can be your credit card, right? It can be your lottery. It can be your free, right? These keywords, whenever my email application observes, it gives a call to the spam application that let's have a look at it, whether it is spam or not. Just because every time, you know, everyone gets an email of winning a lottery from somewhere in Brazil, right? So that kind of thing is possible, right? And my spam application is smart enough to take care of at least 80% of these spam emails. And later on, we also give some training. If suppose a particular email is not a spam and we report it, right? My system will take a call next time whenever that kind of email comes to my inbox, it will immediately throw it to the spam folder, right? So we can definitely write an algorithm for each of the pattern which we observe, right? So your problems for which existing solutions required lot of hand tuning or long list of rules. As I said, rules-based programming in past. Let's avoid it totally, right? So one simple machine learning algorithm can simplify the entire code and definitely will be performing much better than your rule-based programming which was existing. On top of it, in case of the complex problem for which there isn't any good solution at all, I mean, this solution will be definitely based on some traditional approaches which were there in the past. The best machine learning techniques can find a solution, of course. Then, if suppose we have some fluctuating environments, right? These days, if you carefully observe the cricket matches, right? What kind of calculations these algorithms are doing that they are able to predict that, okay, after let's say 50 runs, your Rohit Sharma starts hitting on the onside at a maximum, or let's say at an average of let's say 50 runs, right? So that kind of calculations we can come up with, that in a fluctuating environment, right? Forget about that. Even in case of LBW, right, we take a call based on the third umpire's decision that okay, this ball is going to hit the wicket or not. That kind of thing is also available. Then of course we have something where we get the insight about the complex problems and we have the large amount of data as well. Now the next thing is that how this machine learning works actually, right? So it is very simple. Continuously keep on feeding data to the machine. to start with, you can use a simple laptop. Later on, you can move to HPCs, and then we use these days, we also take care of your GPUs, because we thought that your CPUs are not sufficient enough to take care of the entire calculation, and there is something called as GPU, which is also available with your laptops or desktops. So let's make use of this computation portion as well. So keep on feeding the data, further interpret the data, then understand the useful insights in it, observe some patterns, and then identify the key features to solve the problem. So key features, if I'm able to identify, then definitely I'm once again talking about some of the hidden things which are there in the data, but I'm not able to identify, right? In UP and in few more states these days we have elections, right? So based on the past data plus some extra parameters, every news channel is making some predictions on. In fact, there are news agencies and data agencies who are continuously working at backend in order to predict that who is going to get how many seats and all. So that kind of things are there which are hidden in the data but are not visible to us. But yes, my machine learning algorithms can take care of it. Right. So since we talked about the working of machine learning algorithms, let's talk about training, validation, and testing. Right. So because we are everywhere, we'll be dealing with the data. Right. So this data, the first rule of the machine learning is divide the data. Right. How to divide it? Dividing into training, validation, and test set. Now, the first rule of machine learning is that don't use the same data set for training and for evaluation, right? Why we are saying this, that you should not use the same data set for model training and model evaluation? Because if I want to build a reliable machine learning model, I need to split my data set into training set, validation set, and the test set. And if I don't split it into these parts, then I am building a machine learning model which is giving the results in a biased way. And what I'll get is I'll end up with a false impression of better model accuracy. Right. What basically a model is, what basically these things are, you'll see in the next few slides when I'll finish these data partitions kind of thing. That, see, simply if I'm using the same set of data for training and validation and testing, obviously I'll get a false impression. Every time I'll feel that my model is working correct. So basically, it's a trap if you are using the same set. Right. So we need to carefully divide it, and we need to take care of the cost as well. See, everything has a cost, right? I need to take care of the cost of overall calculation, cost of overall manpower which is there, and taking care of those factors, I'll divide it. So what basically the training data is, let's understand that part. So it is the set of the data that is used to train and make the model learn the hidden features or patterns which are available in the data. Right. So there are some hidden features or hidden patterns which are not visible to me as a human, but yes, my model is going to get trained, right, based on this training data, and I will be able to identify those hidden patterns. Right. For that, you'll study probably in your next session. We'll deal with epochs, right? So what we do is that we feed in each epoch. We give the same training data, and then your neural network comes into picture. So I'll not go into that part. I'll restrict myself to the machine learning, because whenever I'm addressing neural networks, I'm definitely dealing with the deep learning applications and all. So your training should be diverse, should have the diversified set of inputs so that model is trained well in all possible scenarios. For example, let's say This is I'm taking from a very popular course which is available on Coursera. Right. This example I'm taking where let's say I have the home features, right? And obviously I'll have a price. And if I'm only giving the features and if I'm only giving the price of home, then my model may not work exactly, because let's say there are hundreds of features which are there in a home and still the price of this home will be 1 CR. If I'm talking about a city like, let's say, 2-tier city or 3-tier city, let's say Kanpur, right? And let's say this features I'm talking here deals with size as well. Now suppose I'm not giving the location part and I'm trying to predict the pricing of a flat which is there in Mumbai. So definitely my model is not going to give me the correct result. So in that case, I have to train my model in all scenarios so that it can predict any unseen data samples that may appear in the future as well. So the input data will have the features and the pricing of homes which are there in, let's say, a city like Kanpur, also which will have the home features and the pricing for a city like Mumbai as well. Right. So this was about the training data, and to the extent possible, keep on feeding all possible available data. Rest model will take care of. Right. So it's like whatever data is available, relevant data I'm saying, right? It should not be like in case of giving the data for predicting the prices of house, I'm giving the data related to elections, right? And you'll say that sir ne to kaha tha, the model will take care of it, right? No, it should be relevant data. Now, next part is your validation data. So this is basically the set of data that separates from the training set, obviously, right? And which is used to validate our model's performance during the training part. Right. So this validation process gives the information that can help us tuning the model's hyperparameters. Right. What these hyperparameters are, you'll see in your hands-on session that we try to tune those hyperparameters and other configurations accordingly. Right. Number of epochs we change and other stuff. So this is something which is like critic telling us whether the training is moving in the right direction or not. Right. So here I'm going to validate. From the term itself, you might have got an idea that, okay, this is going to help us validate our model. Right. So basically the main idea of splitting the data set into validation set is to prevent our data from overfitting. Right. Now, what basically the overfitting is, I'll cover in the next few slides. That is, the model becomes really good at classifying the samples in the training set, but cannot generalize and make accurate classifications on the data it has not seen before. Right. So some of the things which will become much more clearer when we talk about your overfitting and underfitting, which I've added in the next few coming slides. Now, the last part is your test data. Right. So this is once again a separate set of data that can be used to test the model after completing the training. Because see, once I have done the training part, I have done the validation part, I have taken care of whether my model is overfitting or underfitting. Now it is time to test it. Right? How effective it is. Now the training set should have a diversified set of inputs so that the module is trained in all scenarios and predict any unseen data which is there in future. Right. Sorry, this became the replica of the previous one. Now let me explain with the help of this diagram. And see, everywhere, if suppose I have used any image, I have given the source of it, or else what I have done is either it is created by me. Now, what we do is we train the model on the training set, we evaluate the model on this validation set, and based on this we tweak the model, right? We go for model tweaking or performance tuning, you can say. Right, this is done on the validation side. That would be based on the results which we got from here. Next is we'll pick the model that does the best on the validation set and we'll confirm the result on the test set. Right, so this is the overall picture of your training, validation and your test set. Now, this is something related to your history of machine learning, right? We had this thing from the early 1950s where, Samuel gave in the initial set of slides, we were talking about a definition of machine learning, which was given by Arthur Samuel. So this is the same one who gave a checker player problem where we were dealing with the movement, right? Checker or maybe Chinese checker and several variants are available. Then later on we saw the neural networks where we saw the perceptrons that basically give the idea about combining linearity and non-linearity. Then we have like pattern recognition where we identify a pattern and then take a call. Further, we saw a limit theory came into picture. Then your Minsky paper proved the limitations of perceptron. There is a phenomenal paper which is there on the archive on the limitations of perceptron. Right? They try to identify them. Later on, things were improved. Right? Things were improved as far as perceptrons are concerned. Then we came up with several neural layers, and then your deep learning came into picture. And then if you talk about the late 90s, right, where we started focusing on it, so data mining came into picture. Some of the initially data mining was dealt in isolation. Later on people said that okay, let's bring this data mining under the umbrella of machine learning only, right? Let's bring this data mining under the umbrella of machine learning. Then we started about text learning. We then once again talked about reinforcement learning, which I'll be covering in next few slides. Bayesian belief networks came into picture. When we talk about overfitting and underfitting, the next thing which comes into picture is your bagging, boosting, and stacking. That would be probably covered when your linear regression will be covered. Now, in the 2000s, we saw support vector machines, and later on, the support vector machine, right, was broadly used, and we saw several variants on support vector machines. And then statistical learning came into picture, transfer learning, sequence labeling. So you can see how much amount of updations and modifications these things are happening. And let's now talk about 2010s. We got deep learning systems, right? Now we said that let's use many layers of neural networks. Instead of using a single layer, let's use many layers. So we brought your deep neural networks. Then we got some learnings from big data. Once again, Bayesian's method came into picture. Then these days we have like applications to vision, speech, social networks, and so on and so forth, right? So this was about the brief history, and these days you'll see every now and then we are coming up with some new modifications to the existing algorithms or some new algorithms as a whole, right? Your ResNet architecture, your Google Net architecture, right? Those things are now readily available. Now let's talk about the traditional approach. This was the traditional approach where we used to study the problem. Based on this problem, I used to write the rules. And this was something which was a very hectic thing. Like in some of the problems, you'll find that people took months and months to write the rules, post which the evaluation took place. If it was found to be okay, then the product was launched, or else if some issues were found, we used to analyze the errors. Once again, we used to study the problem, and once again we used to write the rules. Many times we used to get into this vicious circle of writing the rules, evaluating, and then analyzing the errors, and then once again studying the problem. So that kind of thing was also there. And
initially, the old example which I took about spam filters can fit into this. That initially, when only we were restricted to writing rules, then it was easier for spam mails to bypass those rules because there were, just amount of listed rules which can be easily bypassed, right? It is simple, right? Some of the websites are blocked by your university, right? You can go for, VPNs and you can bypass those things. Later on, we got the machine learning approach, right? So this time we said that my programs will be shorter. Instead of writing tons of lines as rules, my programs will be easier to maintain, and the most important thing will be my program will be much more accurate now. So what we are doing in machine learning approach, I'm studying the problem, same thing. After studying the problem, I am using this data to train my machine learning algorithm, right? Then I'm evaluating the solution. If I am satisfied, obviously I'm going to launch it, or else once again I'm going to analyze it, I'm going to study the problem, and once again I'm going to train my machine learning algorithm. Right, so this kind of thing is happening. The only difference between the previous thing and this thing is that instead of writing the rules, I said, with the help of this data, let's train my machine learning algorithm. Right, now, just imagine the current spam filters, much more cleverer, much more effective. Right, so your spam filter using the traditional technique would need to update every time I'll take a care of a flag, right, whether it is a spam or not. In this case, no. Straightforward, no. My system is now smart enough. And on top of it, I have another advantage of using this. And what this advantage is, let's automatically adopt to the change. Right. So every time what I'm doing is I'm training my algorithm, I'm evaluating, I'm launching it, and post launching, once again, I'm updating my data. Right. And this updation will once again lead to better training of my algorithm. A simple regression problem you have, what you do is, let's say you have to predict a stock price. What you're going to do is, you'll use the data of, let's say, last 5 years data, and I'm going to, let's say, I've used this last 5 years data, and today's Friday. Now, for Monday's stock price, let's say this is of, now this stock is listed on NASDAQ, this is Apple stock, right? Apple Inc. stock. Now, for Monday's price, I'll do some prediction with the help of this. Obviously, I'm going to use least square approximation, the simplest possible, or let's say linear regression, which is also called as your least squares, right? This is the simplest algorithm I'm giving. Now, for predicting the Tuesday's data, I'm going to update my data by adding the 5 years plus Monday data. That's how I'm going to improve my machine learning algorithm, which was not possible in statistical approach previously, plus obviously in rule-based programming, this was something which was impossible to believe. Right, so this was about automatically adapting to the change. Now, we saw that these systems are smart enough, it can adopt to the changes. So these machine learning systems can help the humans as well. Just because my machine learning algorithm can be inspected to see what they have learned. In fact, for some of the algorithms, this can be tricky, right? Not for every algorithm, but yet it can be inspected. For instance, right, let's take the same spam filter example. So my spam filter system is now smart enough and has been trained. Now it can easily inspect, and based on some of the list of the words and the combination of the words, it can take a call whether it is a spam mail or something else. But sometimes this relation will, reveal some unexpected correlations on new trends. Right, instead of lotteries, let's say I get an email with the text, "You are lucky today." Right, once again it is talking about some Brazilian lottery which I got for several $1,000. But this time my system is smart enough. This will say, "Oh, once again you are here with a different envelope. Let's drop it to the spam." So I'm studying the problem, I'm training, I'm giving the solution. Afterwards, I'm inspecting the solution. Based on this, I'm understanding the problem better. And if required, I can iterate the same process, right? And obviously, all this is happening all because of an input, which is data, right? We can call it as label, or we simply call it as late data, or based on your, convenience. Now, just, to summarize, machine learning will be great for problems for which existing solutions required a lot of hand tunings, right? And for complex problems as well. So this was all about the base. Now let's talk about machine learning and artificial intelligence, right? Because many people get confused that, okay, you're talking about robots, robot deals with artificial intelligence. Well, how come this machine learning and deep learning is coming to picture? Right, how come this machine learning and deep learning is coming into picture? But no, frankly speaking, your machine learning is a subset of artificial intelligence. Right, so let's formally cover it. Your artificial intelligence is a technology that would enable a machine to simulate a human behavior. Right, this would simulate. Okay, so some question. Can I attempt the lead? Okay, sorry. Okay, I thought it is related. This query is related to machine learning. So that enables a machine to simulate your human behavior. And your machine learning is a subset of AI which allows a machine to automatically learn from past data without programming explicitly. Once again, as I said, I'll be keep on focusing on this particular part. And your goal of AI is to make a smart computer system like humans to solve your complex problems, right? See, everywhere you will find machine learning has gained popularity, right? Previously, if you talk about recommender system, I'll take some more examples. It was dealing with some basic classifications. Now that has also come into machine learning part or deep learning part, where we say that, okay, no, this is something which is, this recommender system is also a part of your artificial intelligence where machine learning plays a role. So basically, AI is a big picture where you will see this machine learning bring deep learning also, somewhere by making a Venn diagram, right? Your AI will be in the outermost part, or it consider this AI as universe, right? And then you will find ML and then part of it under the DL and other stuff. So that's the basic difference between the machine learning and artificial intelligence. Now, these are some of the applications. So once again, I will talk about applications. Once again, we'll focus on, based on the kind of learning we have and the kind of problems we are going to address. So, for estimation and prediction, basically, I give you one of the example of stock market trends. There can be another example of weather forecasting. That would be dealing with your machine learning, right? This is one of the popular applications, right? Your Meteorological Department of India, IMD, right? Or sorry. So entire weather forecasting depends on machine learning plus on top of it the experience from the past. Then you have language processing, right? Text to speech, speech to text, speech recognition, robotics, the arm movement, right? A simple arm movement of a robot that deals with tons of lines of machine learning code. So forget about the entire movement, just the arm movement itself becomes very tricky. Then we have like self-driving cars, you know, a bus thing, drones. Then we have like vision processing where you'll find computer vision once again gaining a lot amount of interest. You'll see that these days computer vision has become a subject, like somewhere in some of the universities you will find it as an elective, somewhere you will find that this as a program core. Then we have in the healthcare as well, you can find the application of. These are some of the state of art application of machine learning where you have your autonomous cars, right? In US, right, especially in California state, you'll find lot many autonomous cars running. Tesla focusing on autonomous car, Google focusing on autonomous car, where you'll see lot amount of OLTP, computer vision. But with OLTP, I mean to say online transaction processing, because continuously your car will be taking data from your maps and then processing about the traffic and the movement of the vehicles, computer vision, right? So everything will fall for this thing just because this is something which is a state of art application. Speech recognition, yes, once again, voice to text and text to voice, which I've already covered. Now let's talk about types of machine learning. So basically, it is classified into three. You will say that heading says three, but in this you find four, just because what I've done is I've introduced this part as well. Normally, people don't talk about this semi-supervised learning. Everyone talks about big picture, right? That there is something which is called as supervised learning. There is something which is called as unsupervised, and there is something which is called as reinforcement learning. Right? For supervised, we have like classification problem, regression problem. Here we have like clustering and association, and along with that association and anomaly detection. Then we have like reinforcement. Now let's formally talk about supervised learning. Right? Now there is something. Sorry. Once again, I got stuck into this. Sorry for this interruption. Let me get back to it. Yeah, came back quickly. So, in case of supervised learning, what we are doing is we are giving training data and your desired output as the input, right? So what I'm trying to say is that in case of supervised learning, let's say on this side I have some inputs, on this side I have output, right? So I'll be giving both as an input, and we teach the machine using this labeled data. So to make the things much more clearer, that means if suppose I am giving, let's say, some images as an input, I'll also tell that what this kind of object it is. I'll also tell what kind of object it is. If I'm giving initially some audio as an input, I'll give, along with that, I'll give the text transcript initially. Right. initially. Later on, I'll expect from the system to behave in a way that I should also get some output. So once again, let me explain you in a different way. From this term itself, we got an idea that here we have a supervisor, and this supervisor is nothing but this training data and output data. This training data is nothing but the combination of your, all sorts of inputs. And using these two, we'll come up with a model with the help of some learning algorithm. So what I'm trying to say is, I'll have some input, some associated output, some input, some associated output, some input, some associated output. And I'll pass on this to the learning algorithm. And this will give us a model. To this model, what I'll do is, to this model, I'll give some new input and I'll get some output. Right, here this input output is nothing but your training data plus your desired output. Right, initial setup that every time, because see, supervise, I'm giving some supervision well in advance. I'm giving some supervision well in advance. So in this case, what we do is, we have classification problems and we have regression problem. In case of classification, basically it is about predicting a label or a class. Right, in case of classification problem, what we are doing is, we are trying to predict a label or a class. And in this, we get some discrete valued output. Right, in this we are getting some discrete valued output. That means if suppose I have this training set where I have these emails, along with that, I'll say that, okay, this mail is okay, this mail is okay, this mail is not okay, that means spam, spam, spam. And based on this, I'll get some new instance, my training is done, and now it will take a call that whether this particular email is spam or just a simple thing. Right, so here what we can do is, we can take care of risk evaluation. I can forecast some of this sales based on your supervised learning. But in case of classification, it's like I'm giving some discrete value that, okay, let's say I have given, and let me take some other example where I have given good number of inputs in terms of, let's say, fruits, right? Later on it will identify that, okay, based on, and this identification, this thing you should note, this identification is done based on the labels which we have attached previously. Right, so this identification is done based on the labels. Now this was about classification problem. The next thing can be your regression problem. Right, in case of regression, it is all about predicting a continuous quantity. Right, so this regression is basically a predictive analysis which can be used to predict some continuous variables. From this figure, you can say that, okay, I got, some values, and then based on some, regression algorithm, I'll get the value for a new instance. How close or how far this thing is, that would be, based on how effective my model is, and how my bias and variance are working. What basically the bias and variance are, that would be clearer in the next few slides. So here what we can do is that logistic regression can be, one of the things which can be used for classifying the output as a value to the corresponding based on the probability belonging to some given classes and so on and so forth. And this classification and your regression problem, my aim is almost to forecast the outcomes in both the cases. Right, that means, because see, here what we are trying to do is, I am trying to train my system with the help of these inputs and outputs. I am coming up with this model. See, recall the discussion where we said that, okay, I'll fine tune it, right? So based on this input and output, we got the learning algorithm with the help of which I got a model. I can fine tune this model, and then ultimately what I'm expecting is a new input will be passed on and I'll get the better output. And how close it is, that would depend on how better my model is. So this was about classification and regression, which is under, supervised learning. And as I said, there is, another another thing which is called as your semi-supervised learning, where, what we try to do is we try to add some training data along with some few desired output, not all. That means my algorithm can deal with partially labeled training data. Right, my algorithm can deal with partially labeled training data, and usually a lot of unlabeled data we get, and we get little bit of labeled data, especially if suppose I'm getting let's say a data, and even after cleaning I get a partially labeled data set available. So in that case I'll say that, okay, let's go ahead with semi-supervised learning. And for that, we have some of the semi-supervised learning algorithms where we can have algorithms like deep belief networks. Probably you might be covering in some of the sessions about deep belief networks as well, right? Which is called as DBNs. And we can have your Boltzmann machine. Your restricted Boltzmann machine can be a very good example for semi-supervised learning, where my application will be able to my model will be able to deal with partially labeled data. Now next category is your unsupervised learning. So in unsupervised learning, only your input is provided, right? And there isn't any output which is supplied as a label. So in this, what I'm saying is my training set will have all these input data, right? It can be, let's say, I have provided images of animals. Now, with the help of some clustering algorithms, whether it is k-means, db-scan, or whatever, I'll take a call that some of these things will be cat, some of these things will be rats, some of these images will be dogs. Now, one thing is, since I have not provided any label, my system will not come back and say that, okay, this is the image of a cat or this is the image of a rat. But my system will come back and say that, okay, this is a set of images which are similar. This is a set of images which are similar. And so it means clustering is done. Right? In some sense, clustering is done. So in case of unsupervised learning, from this example, you might have got an idea that we are discovering the underlying patterns. Right, we are discovering some underlying patterns. Now, in unsupervised learning, we said that, okay, training data is given without the desired output. And this unsupervised learning allows us to approach problems with either little or no idea. Right, because I'm not sure what our result should look like. That would be with the model. And obviously, this machine will be trained with unlabeled data. So clustering can be, one of the clustering problems can be under unsupervised learning, your anomaly detection or novelty detection, or even association problems. Your association rule mining is one of the examples, right? In that case, what we can have is we can have, in case of anomaly, we can have one class SVMs, we can have isolation forest. So in case of clustering, that would involve, target marketing, and in case of association problem, it can involve, discovering the patterns, finding some co-occurrence, and there can be, let's say, I can identify a pattern, or you can call it as a co-occurrence as well, that whenever a person goes to a supermarket and buys bread, there is a high chance that the person will also buy butter or jam, or sometimes both. Right, so this is a pattern which has been observed based on the sales made in a supermarket. So as a person, if I'm sitting at the counter, I'll not observe how many people are buying what all things. But if I have the data of the sale, my model will be able to identify the gem which is hidden in this data. So that kind of thing is done in your machine learning. So clustering, I gave you this example that I'm able to identify that this is, let's say, set of cats, this is set of rats, this is set of dogs, this is set of goats. But yes, my computer will not say that, okay, this is cat. It will say that, okay, these are the set of, at the initial, so right, I can make my algorithm function in that way also, that it will declare that this is cat. Initially, I'm trying to explain you that as a system, it will say that these are the three different identities, but what these things are, that I don't need to declare at this moment of time. Right. So for your visualization algorithms, these algorithms are perfect examples of your unsupervised learning. Right. You keep on giving 2D data, 3D representation, and then the plotting is done. Now, anomaly detection or the novelty detection. So here, in healthcare, you will find this thing coming into picture. In case of anomaly detection, what we try to do is that, or the novelty detection, what we try to do is we try to detect something unusual, right? So in these days, a lot amount of research papers are there in for predicting COVID diseases. What they do is they take images of lungs and X-ray images, and then they take a call that okay, this gives an idea that okay, based on my algorithm, there is an anomaly detected, and this particular X-ray image is of a COVID patient. Another example can be your credit card transactions deals with this anomaly detection, where they try to catch some of the issues. Let's say even your Gmail, right? If suppose you have enabled two-step verification, or your internet banking is there, if your banking system or email system observes that you are trying to log in from a different, totally new IP, immediately it will send an OTP. Just because a pattern has been detected that there is an anomaly. Right, so that kind of call your system takes, its automatic call, no human intervention is there. And another thing is your novelty detection, right? So in this, your difference is that here my algorithm expect to see only normal data during the training, right? So in case of anomaly, I'm trying to identify the unusual thing. In case of novelty detection, I'm trying to observe the normal data. That's the only difference. There is another thing which is your association rule learning, right? Where my goal is to get the details about large amount of data, right? Let me write it. This term, everyone should be familiar with this. Association rule mining. So here it's like I am digging into large amount of data and I am trying to discover some interesting relation between the various attributes. Right, my supermarket example is one of the potential example of association rule mining, but that there is some association with your bread, butter, and jam. Right, many times you go ahead with buying a particular product on Amazon, immediately you will see that people who bought this also bought these items. Right, so once again your recommender system is coming into picture here. So this was about your anomaly detection. Next is your reinforcement learning. So this deals with this deals with your rewards and penalty. So rewards from the sequence of actions, and in this your agent interacts with its environment by producing actions and discovering the errors or rewards. So this can be observed in gaming. So here reinforcement basically means to establish or encourage a pattern or behavior. And in this, your input depends on the action we take. Along with gaming, your robot movement is something which you can consider. Right. Here, what we say that we don't know anything. Right. Let the system learn. Now, this is something which is once again important. Learn the series of actions. How it has to deal with the situation and the environment, let it learn on its own. Right. I am giving you an example of, let's say I have an agent which is a robot. If this is the environment where you have two things, right? On this side, it's like a fire is there. On this side, a bucket is there. So if it goes to this, obviously there is a penalty, right? And from here, my system automatically got to know that not to move in this direction. There is a reward. Sorry, there is a penalty, right? So what we do is we observe, we select the action using policy, we go for the action, either we get a reward or a penalty. Once again, we'll update the policy. That means next time don't go towards this side, and learn, iterate until an optimal policy is found. Right, the robot movement, or even these days you have your toys where a smart car is there, and that takes care of all the hurdles which are there on the way, and takes a next turn, whether it is right turn or left turn, and moves forward. That's something which is your reinforcement learning. So these are some of the applications for supervised learning. Your risk evaluation, your forecasting of sales, weather forecasting. These are some of the applications of supervised learning. And also, from these examples, you recall the previous discussions. In case of supervised learning, we said that there are like regression problems. Right? Regression will be dealing with a series of data. So obviously, in case of weather forecasting or share price prediction, I'm dealing with a series of data. So definitely, it will be a regression problem, and obviously it will fall under your supervised learning. In case of unsupervised learning, we said classification is there, right? So obviously your recommender system is one of the examples where, let's say you get a recommendation of a product or a movie, right? That is based on the inputs from various people, and there isn't any labeling, right? There isn't any labeling. Then we have like reinforcement learning where we have like self-driving cars, we have gaming, right? Robots, and so on and so forth. These are some of the examples of your various applications. Now, next is we got to know. Yes, sir, definitely. I'll be sending the PPT, entire notations. You might have observed that whatever I am inking, that also I am saving. So definitely, I'll be sharing the PPT as well. Yeah. So next is your bias and variance. This is something which is once again very interesting topic, because we talked a lot about machine learning, and now we talked about various algorithms, problems, and so on and so forth. But the problem is how to analyze that my model is working fine or not. In that case, I have something which is called as bias, and I have something which is called as variance. Right. So your machine learning is increasingly used in applications, and with larger data sets and various implementations with all sorts of possible algorithms and learning requirements, it becomes even more complex to create and evaluate these models. And since all those factors will directly impact my overall accuracy of the model, that means what kind of model I have, whether it is accurate or not, which gets further skewed by some false assumptions, some noise, because data is not always crystal clear. It will have noises. I'll give you some data sources in next few slides where you can get a feel that okay, data is always noisy, at least in 99.9% cases. Then some noises will be there, some outliers will be there. So your machine learning models cannot be a black box, and your user needs to be fully aware of the data and the algorithms to trust that the outputs and the outcomes are worthy of it. And any issue in the algorithms or with the polluted data set can definitely impact my machine learning model. So what we have is, we have something called as bias and something called as variance. So let me give you an example of, let's say I have this kind of setup, where on this side I have weight of some people. On this side, I have height of some people. And what we have is, we have some data points, right? Obviously, with increase, there are chances with increase in, with increase in weight, height will also be increasing, and after some time, height will not increase. So you'll find data like this. And out of this data, we'll have some training data and some testing data, because we know that from this data set only we got to know that we have to bifurcate into training, testing, and validation part. And what I know is that there will be a true relationship in height and weight in a form of something like this. But this is the true relationship. But what will happen is that my machine learning algorithm, let's say I'm using linear regression, or you can call it as least square approximation, or simply least squares. So this will give me a line of something like this, or maybe something like this. It will not going to fit to this ideal line. Another option is that I can come up with this kind of line. Now this will match everything. But I know that this is forming the true relationship. This is forming the exact relationship. Sorry, I made an error. Yeah. This is the exact relationship. This is the true relationship. So my straight line is deviating, right? There is a bias with this true relationship and the exact relationship. In that case, my straight line will give some good prediction, right? Based on your least square approximation, I'll get some good prediction, but not the exact prediction. Or you can say not only exact. Why to take exact? Exact is something which is not possible, right? We'll deal with probabilities, we'll deal with near values, right? We'll not get the great predictions. And definitely there will be a difference, right? So difference between your data set in the fits of these is called as your variance. And the distance which I'm maintaining, basically, bias is something which is a phenomenon that skews the relation of an algorithm in favor or against an idea. So your straight line has low variance because, from straight line, I'll definitely try to get the squares of difference. So, and that's what we do in linear regression. That would the picture will be very clear in your next section, which deals with probably your least square approximation only, or the linear regression, because some of squares are very similar for different data sets, and your straight line can give, definitely we got that good prediction but not the great prediction. So here comes the picture where in the training set I'm getting the bias and variance. So let's formally talk about bias and variance. So bias is a phenomenon that skews the result of an algorithm in favor or against an idea. And this bias is considered a systematic error that occurs in the machine learning model itself due to some incorrect assumptions in the machine learning process. Technically, we can define this bias as the error between the average model prediction and the ground truth. I hope now the things might be much more clearer. So basically, there is a difference between the average model prediction and the ground truth, and that is the error, which is your bias. So it describes how well the model matches the training data set. So a model with higher bias would not match the data set closely. Higher bias means my model has issues. A low model will closely watch the training data set. Right, sorry, match the training data set. That means low bias means my model is good. Now, there are some characteristics of a high bias model. So if suppose bias is high, my model is not good. That means my model fails to capture the proper data trends. And there is a potential towards underfitting. What the underfitting is, I will explain in next few seconds. And we have like more generalized or overly simplified model. Obviously, I'll have high error rate that would lead to high bias. Now, the next thing is variance. So variance refers to the changes in the model when using different portions of training data set. Right, in my example, if I'm, instead of this, I'm applying for this, then there will be a change. So variance refers to the changes in the model when I'm using different portions of the training data set. In simple words, variance is the variability in the model prediction. How much the ML machine learning function can adjust depending on the given data set. So variance basically comes from highly complex models with a large number of features, and this models with high bias will have low variance. Models with high variance will have low bias. So there are some characteristics of a high variance model, which includes like noise in the data set, potential towards overfitting. Don't get confused. Wait for a few seconds. Then we have like complex model, trying to put all data points as close as possible. Right. So here is something which is I thought I'll clarify. So in some of the algorithms, like linear regression has high bias but less variance. Your decision tree has low bias but high variance. Right. Then your bagging and other things comes into picture. But before that, let's look into underfitting and overfitting. So your term underfitting and overfitting refers to how the model fails to match the data. The fitting of the model directly correlates to whether it will run accurate prediction from a given data set. In case of underfitting, this will occur when the model is unable to match the input data to the target data. This happens when the model is not complex enough to match all the available data and perform poorly with the training data set. That means what I've done is, in this case, in underfitting, it is not matching, right? And the model is not complex enough and it is not able to match even in case with the training data set. In case of overfitting, this relates to the instances where the model tries to match with non-existent data. So here it is like there is a mismatch. Here it is that something else, something random has popped up. Right. So this occurs when dealing with high complex models where the model will match almost all the given data points and perform well in training data set. Till the training it was fine. However, would not be able to generalize the data point in the test data to predict the outcome accurately. That means in the later half, my models is not predicting properly, so I have declared it as overfitting. Right, so this is the difference between underfitting and overfitting. So there is a trade-off between bias and variance, right? So bias and variance are inversely connected, and it is impossible to have a machine learning model with low bias and a low variance. That's something which is not possible, right? So we have to find a way in between, and that's how your regularization, boosting, and bagging comes into picture. Don't worry, I'll not throw light on this. I know I'm already running short of time, so let me quickly finish these things. Yeah, these are some very important slides for you guys because I've gone through these resources for any particular project or research. If you are, running short of data, these are some of the open data repositories, right, where you can get the data. And for Indian data, this is the best website probably, where you get anything and everything from, population to the education index and whatnot. Visit this site. This is a very wonderful site. You will get lot many ideas, because when you have the data, you will get the idea about, dealing with the problems. Right, these are some of the various function representation for numerical functions. We have like linear regression, we have neural networks, we have SVMs. For symbolic, we have like decision trees, we have rules in proposition logic, rules in first order predicate logic, right? FOPL and all you might have heard about. Then I'm just simply giving the names because these things will be, your naive-Bayes Bayesian networks, hidden Markovs, and these things will be covered in your probably in your next session. And then we have like for search or optimization of the algorithm, we have gradient descent where we use perceptron and back propagation algorithm. For dynamic, we have H&M learning. For divide and conquer, we have decision tree. We have rule learning. For evolution computing, we have like genetic algorithms, right? And then we have genetic programming and neuro evolution as well. And then we have like accuracy, precision and recall, squared errors or mean squared errors, likelihoods, your posterior probability, and divergence. Yes, these things are there to evaluate the things. No, probably this is all. This is a reference, and probably this is all from my side. Let's take some questions now.
Okay, so thank you, sir, for a wonderful session. So now I would like to ask anybody from the participants, in case if they want to ask any questions, so they are free to go ahead. So are there any questions from the audience and the participants attending this session? It seems there are no questions, sir.
Yeah. Okay. Thank you.
So thanks a lot for a wonderful session. So I would like to request you that you could share the PPT to the mentioned email address. So we could, yeah. Okay. So thanks a lot, and thanks everyone who joined the session. So just for the information, the next session will be at 3 to 4:30. So we'll meet accordingly.